let's quickly look at the tree of life as we know it right now. That's been developed by the work of Carl Woese and his colleague Fox, who developed this whole method of organizing the organisms that we see on Earth using the 16S or 18S RNA gene, which is the ribosomal RNA gene. So at the base of the tree, you can see this LUCA, and we talk about LUCA where we mean the last universal common ancestor. So this was the organism that is pointed to by all of the 16S and 18S genes when you look at their relatedness. It seems to point to a point at which one organism was the actual forerunner for the rest. So the main thing I want you to note here is that you've got three domains. You've got bacteria, archaea, and eukarya. And these three domains, they merged at different times. And this is the main thing that I want you to note about the structure of the tree, that you've got branches and you've got different lengths of branches, different points at which the branches come. And if you follow the tree and you notice when each branch actually comes, like this is the first branch we see, then you see this branch, and then you see the rest of these. So eukaryota is basically this area over here, which includes the humans. And over here, as we go back in time, you have bacteria and archaea. And the depth of the branch, or how long the branch is, also describes some information and where it comes. So as we make trees which actually have scale bars here, they'll be able to show you in terms of molecular time, that is using the concept of the molecular clock, how far ago in time when certain divergent events happened. So when did this particular branch divert from its originator into these two organisms? So that's basically what we're going to do as we look and understand how to build a phylogenetic tree. And as we look at the 16S RNA gene sequence, the hypervariability in those sequences is what gives us the position of all these different organisms. So when you get the 16S gene of Haloarchaea or a member of the purple bacteria, and you compare it to the member of the Thermococcus or Methanococcus, you'll see that it's still the same general gene, but it differs on specific places, and those differences are what give you this branching pattern. And the time when those actual differences occurred is how far back those particular organisms emerged. So that's basically how we use the tree of life to be able to look at the relationships of organisms in terms of phylogenetics and the molecular clock.